Welcome friends. In last few weeks we have made certain knowledge in the frequency domain of the control systems. Let us today have a recapitulation of what is our understanding upon this. So we shall focus on the following points: the resonant peak, resonant frequency, bandwidth or half power frequency, cutoff rate, gain margin and phase margin. So let us summarize the points one by one, starting in the resonant peak. So resonant peak, we have studied the control systems in the frequency domain, and if I speak about the Bode plot, we can say that a system which is higher than the first order system can be represented in magnitude plot as like this. So we can have a system like this, we can have a system like this, and we can have a slope after some time like this. So this can be a slope of minus 20 decibels per decade. Then this can be a slope of minus 40 decibels per decade. Or we can have something, this is omega or omega by omega n. Or we can have a magnitude plot, this is magnitude in decibels. So we can have a magnitude plot like this. This is a straight line, and after certain frequency we get a slope like this. Or we can have a plot like this, and we can have a resonant peak like this. It can be a combination of different type of plots. So whenever we are plotting a response and we get at certain point, there is an abrupt peak like this here. So such peaks in the gain, you can understand that this will disturb the system all of a sudden at certain frequency. So this frequency where the system will have a sudden gain or hike in the gain, this frequency will called as resonant frequency, and this gain can be called as the resonant magnitude or resonant peak. So there could be systems in which we have more than one such kind of peaks like this we can have. So there are, in this figure there are two resonant peaks. So there will be two resonant frequencies, omega r1 and omega r2. So this kind of situation is very common in control systems or in any other system wherever the system order is more than one. When the system order is greater than one, then such kind of resonant peaks can be experienced. And in control systems, this is the challenge for a control systems engineer to attenuate such a peak, because if such a peak is there, then system will have sudden unwanted gain. This may cause to the instability of the system for all. So that is why we keep on studying about the resonant peak of the systems. Going further, if I say that there is a half power frequency, so in most of the situations what we studied, there are situations when we have a gain, and this is the gain of the system for a long time, then there is a fall in the gain. This is quite possible. So in a causal system, which is an actual system, we always have a system in which we have a system where we have a constant gain for some time, Then we have a fall in the gain. So as we discussed earlier in previous lectures, these are the two asymptotes which are combined to make this final plot, and this is the frequency where we will see that the system power will be half, so half power, and so the magnitude of the voltage associated with the system or gain associated with the system will be 1 by root 2. So here we will see that an error of 3 decibel will be recorded. So such a frequency of the system will determine the corner frequency of the system as well as the bandwidth of the system. So system is said to be having a bandwidth from very low frequency to up to the half power frequency. This is the half power frequency. So most of the control systems will work happily within this range, while when the system crosses this frequency, you will see that the gain is gradually reduced. Suppose I take an example where this is a 0 decibel line. This is the 0 decibel line. So this means the magnitude, absolute magnitude is 1. So for a system, if the gain of the system for this frequency range, if the gain of the system is 1, this is the gain magnitude 1, this is the gain magnitude. So if I give an input of 5, the output will be 5. Correct? Then if we go to a higher range of frequency, then what will happen? Say I am having a slope of minus 40 decibels per decade. In that situation, what will happen? That after 1 decade of frequency, so if this is a normalized frequency, then I have 10 power 1, 10 power 2. So reaching here, I will see that suppose the slope is minus 40 decibels, so the value will be minus 40 decibels here at this point. So at frequency omega equals to 10 power 2, we will see that the magnitude is minus 40 decibels, that is 20 log base 10 magnitude m. If we want to solve for m, we will see that m equals to 10 power minus 40 by 20 equals to 10 power minus 2. It means m equal to 0.01. So in that situation, if the gain becomes 0.01, then the output for an input of 5 will become 0.01. So in a practical situation, such kind of fall of output or fall of gain will result in recording nothing but some value very much near to 0. So in certain approximations or in certain instrumentation systems, if you are giving an input of 5 and output is coming as 0.05, so it will be recorded as 0. It will be approximated to 0. So such a gain of the system is not useful in practical situation. It means we are not able to control the output of the system, because when the output of the system falls to such a low value, then that output is of no use. So that is why we will consider working with a system when it is within our frequency range of interest, and that is why this range is also called as bandwidth. This is the bandwidth. Now going a little further, when I was asking about the cutoff rate, so I'm again speaking about the second order system with fall of the slope after a frequency. This is the bandwidth of the system, and this is minus 40 decibels per decade. So this frequency is actually your cutoff frequency, and this region around the cutoff frequency is called as the cutoff rate, because this rate minus 40 decibel per decade is the rate at which the system gain is falling from 0 decibel per decade, from 0 decibels per decade to minus 40 decibel per decade. So in most of the control system design, we avoid such a design where there is sudden fall of the gain at this rate. We will prefer to design a control system in which you have a 0 decibel gain, then it should have a minus 20 decibel per decade slope, then it should have a minus 40 decibel per decade slope. So this should be the design of the control system in most of the practical situations to save the system from such an abrupt jump of the gain, because with such a fall of gain or rate of fall of the gain, system will have a resonant peak like this. So to avoid this, we have to avoid this kind of situations. So that is why the study of the cutoff rate is very much important in control systems studies. So going further, we are talking about the gain margin. So gain margin, so again for the sake of simplicity I will write to plot a graph in which the system will have a relative stability, then a gain margin can be obtained at the phase crossover frequency. So this is the omega crossover phase. So at this frequency we obtain the value of the gain. For a stable system, this point should be always to the right of the -1 point. This point we'll discuss in another lecture where we'll elaborately discuss about the Nyquist stability criteria. So here for stability of the system, so the crossover of the negative real axis should be as far as possible from the -1 and it should stay on the right of the -1. So going further, if we speak about the phase margin, so we should always say that phase margin is acquired at the gain crossover frequency. So this magnitude of 1, which is the radius, so this should be crossed in such a way that the crossing point of the gain magnitude 1 should provide us with the gain crossover frequency. So this is crossover gain. So at this point we can obtain the phase margin of the system, because if this point comes in the first or second quadrant, that is in this quadrant or in this quadrant, the system is unstable, while if it comes in the third and fourth quadrant, then the system is stable. So these are the various performance specifications in the frequency domain, and in a later session we will discuss about the relationship between the time domain specification parameters and frequency domain specification parameters. So to brush up what we have studied so far, let us have some quiz. So let us have our first quiz. The following system model are absolutely stable. So those who are watching this video and listening to my lecture, they can see the quiz and have a pause before they really go to see the answer, because quiz is for analyzing your knowledge and coming to the right conclusion. So what are the systems? First system is your 1 by tau s plus 1. The second system, here comes 1 divided by 1 divided by 1 plus tau 1s into 1 plus tau 2s. Third, 1 divided by s into tau s plus 1, and the fourth one is 1 divided by s into tau 1s plus 1 into tau 2s plus 1. So we have 4 transfer functions, and let us see which of these transfer functions will give us an absolutely stable system. So for that, we would better go for the polar plots. So the solution, we go for the polar plots. The polar plot for the first one should be like this, as we had studied. I'm not dividing the axis for the sake of saving time. The second one should have polar plot like this. The third one should have polar plot like this. The arrow should be there to understand where is the frequency omega equal to 0 and where is the frequency omega is infinity. So it is coming from omega equal to 0. So let us find out which of the transfer functions are absolutely stable. So the condition for the phase margin and gain margin is that both should be positive, and the system phase should lie in the third and fourth quadrant. In this case, the system is in the fourth quadrant, so this is stable. In this case, second case, we have system in the third and fourth quadrant, so it is stable. In the third case, it is in the third quadrant, so it is stable. And in the fourth case, unfortunately, this goes to the second quadrant and third quadrant, so that is why we will have a phase margin which is not positive. And for seeing the gain margin, we have to find out where this gain goes actually beyond the -1 point or not. So we can understand that here we have 3 correct answer and only 1 wrong answer. So let us go a little ahead to the next quiz. We have quiz 2. Quiz 2. A transfer function model is absolutely stable. A transfer function model is absolutely stable if the phase phi is number 1, 0 is less than phi less than -90 degree. Number 2, -90 degree is less than phi is less than -270 degree. Number 3, 0 is less than phi is less than -180 degree. And number 4, we have -90 degree is less than phi is less than -180 degree. So as we have discussed that for a stable system, the system should lie in the third and fourth quadrant. So naturally the option which comes for us is number 1, this. The second option which comes for us is this one. This goes the second one here, it goes into the second quadrant, so we reject it, and again this goes in minus 90 to minus 180 degree. So again we find it okay for our requirement. So we see that the system with option 1, 3 and 4 satisfy of our requirement of absolutely stable. And with this, let us go to the next quiz. Quiz number 3. So what should be the loop transfer function for the polar plot? What should be the loop transfer function for the polar plot? Let us see. What is the polar plot? For simplicity, I am not giving nomenclature to the axis, that is real and imaginary axis, but I am directly drawing the polar plot. Let us see the third quiz, where we draw a polar plot like this. So this is the arrow, this is the arrow. So we'll find out the right transfer function which can give us the plot like this. So the first transfer function is 1 divided by s into tau 1s plus 1 into tau 2s plus 1. The second transfer function is 1 divided by tau 1s plus 1, tau 2s plus 1, tau 3s plus 1. The third transfer function is 1 divided by s square tau 1s plus 1, tau 2s plus 1. And the fourth one is 1 divided by s square tau 1s plus 1, tau 2s plus 1 and tau 3s plus 1. So we have the 4 transfer functions and we have to identify which is the right polar plot. So let us start with the example of, say, this is the polar plot of a function. So we understand that this is 1 by tau s plus 1. We have another plot like this. So we have 1 by s into tau s plus 1. So we go a little further and draw a plot like this. So this is 1 by s into tau 1s plus 1 into tau 2s plus 1. Now if I want to plot a function like this, so when we try for the next one, which is in such a way that we are plotting the starting point shifted by 90 degree like this. So in this case, as we see that the starting point at omega equal to 0 is shifted by 90 degree, so we will have a transfer function written in the form s square into tau n s plus 1 into tau 2s plus. Now going little ahead, if we start from the same point and terminate at further 90°, so we can have the change of the factors like tau 1s plus 1 into tau 2s plus 1 into tau 3s plus 1. So you can understand how with the change of the pole at the origin, that is S, or the pole at some other point, will affect the plot of the polar plot. Both the changes at omega equal to 0 and omega tends to infinity can be recorded with the change of these factors. So with this, the discussion of today on the revision of the parameters of frequency domain analysis and the polar plot is completed, and we shall come with closed loop frequency response in the coming lecture for detailed discussion. So friends, this is the textbook by Professor M. Gopal on control systems. We can refer to it and see more problems. At the end of each exercises, there are objective questions also for your reference. Similarly, these two books are also having exercises and important questions to practice. So if you have liked the session, give a like in the YouTube and subscribe the channel, set the bell icon and get the notification for the next video. So you can write me to my email ID controlsystemsfaq@gmail.com. Thank you for your patient listening.